Ora si registrerà la conferenza.
Okay, so welcome everybody to this Train the Trainer session within the ENTRAIN project. As all of you know, I think ENTRAIN is an Interreg Central Europe funded project. It focuses on, let's say, improving the air quality at local level through the use of small district heating networks run based on renewables, renewable energies. And we have 5 pilot regions where we are trying to implement this solution. And within the project, one of our core activities is training. We have both training at local levels in the national languages, of course, but we also have an international, let's say, program or training program, which is basically the idea of training the trainers. And within this Train the Trainer session, we also welcome, of course, external guests. So as in this case, I am happy to have here guests from Kosovo and from Italy, so external to the project. So welcome, and I hope you will enjoy this session. I also thank the speaker, of course, who accepted to be here today and to allow us for a fruitful session. And let me also thank the Austrian partners for organizing these sessions. This is the 3rd session we have, and we are foreseeing 2 more. So also please stay connected with the project to know about these opportunities.
Yes, we can see it. Can you?
Okay, I will try to start it in the presentation
Okay,
mode.
perfect.
So
Yeah.
it should look good for you.
That's good. It's good.
Okay.
Thank you.
Very good. So the technical points are working very fine. So okay, good morning once again. My name is Joachim Kelz, as Heidrun mentioned before, and I would like to give you an overview on emissions and air quality. My speak is divided into these 3 main sections. So at the beginning, we talk about the main impacts on the emissions and the air quality. After that, we concentrate on the question how we can reduce the emissions. And finally, I would like to give you some ideas for an efficient operation of heating plants combined with reduced emissions. So if this fits fine for you, I will come to the first part, and let's start with the main impacts on the emissions. Here on this slide, you can see the main parameters influencing emissions and the air quality in general. So what are the important or crucial things we have to look about and to talk about? At first, the fuel properties. As you know, there is a big range of the quality of the fuel used in heating plants. When you think about the water or the moisture content within these fuels, or also the chemical characterization of the fuels, there is a quite broad range of availability. Then the second parameter is dealing with the temperature during the combustion processes. So as you might imagine, the temperature plays a relevant role for the combustion and also for emission processes during the whole combustion process. Then another relevant parameter is the mixing of the flue gases in the furnace or in the combustion boilers. So here we talk about the turbulence of the flue gas and the distributed air of combustion. Then the 4th main parameter I want to mention is the residence time of the flue gases. So it depends on the time where the flue gas or the emissions are in the combustion zones. I would like to come to this point a little bit later. And finally, the process control is also a relevant parameter, because you need an appropriate control system to run your system. So just to remember for the whole session or presentation, the 3 T's, they will be very important in the further course of the presentation, and this is the time, the temperature, and the turbulence. Yeah, when we have a closer look on the combustion process, we know the 4 different stages of combustion, namely the drying process, the pyrolysis process, the gasification, and the combustion process. And I will just show you. You should see a kind of laser pointer now on the slides. When you have a look at this picture, the fuel comes into the combustion chamber. In the primary combustion chamber, we have first this drying process. So the wet fuel is first dried on the grate. After that, the second step, the pyrolysis and gasification processes are starting when the temperature is high enough. And at the end of the process, we have this so-called combustion, and this combustion process can be divided into the charcoal burnout combustion. The charcoal burnout leads to, or a good charcoal burnout leads to high efficiencies of the fuel used. And the quality can be quantified due to chemical analysis of the ashes. For example, analyzing the total organic compounds or total inorganic compounds which are remaining in the ashes. And the second process when we talk about combustion is the gas phase combustion. And also the gas phase burnout or quality is relevant for both the efficiency of the boiler operation as well as for the emissions. And also this so-called gas phase burnout quality will be still an important topic within this presentation. So also remember this word, gas phase burnout quality. You will hear this in the later on in the presentation. Okay, I will go to this quick. You all see or know the different combustion technologies which were implemented. I will just say that in Austria we are dealing with mainly fixed bed, or often deal with fixed bed combustion system. Fluidized bed combustion are systems for high thermal output, let's say 10 megawatt and more. And typically in Austria, we are focusing on these fixed bed combustion systems in district heating plants. Okay, I hope you don't get shocked when you see this picture. I don't want to go through to all these chemical processes which are depicted here, just to show you a few points. And there is a conflict of interest. Maybe we can start with this. On the one hand, biomass is seen as a renewable and CO2-free energy source. But however, emissions occur during the combustion process, and there is this difference between the emission and emission as well as the air quality, and here you can see the emission. Here during the combustion processes, some chemical reactions took place, and this leads to emissions. Then here in the chimney or somewhere else in the combustion system, we are measuring these emissions. And the emissions are divided into two fractions. First fraction is the particulate matter emission, so the solid phase, and then we have gaseous emissions or pollutants. These are depicted here on this slide. And we can distinguish between complete combustion and incomplete combustion processes. So the complete combustion leads to these types of emissions, and the incomplete combustion processes leads to these types of emissions. And the crucial point here I want to show is that after the chimney, when the flue gas is released into the atmosphere, then some other chemical processes are starting, and there are a lot of different boundary conditions and reactions going on, and the flue gas is cooled by the atmosphere or ambient air. And then we talk about emissions, and these emissions are influencing the air quality. So when we deal with this topic, it's important to know the difference between the emission and emission, and what are the impacts on the air quality. On this slide, you can see a very important parameter also when we deal with the emission during combustion processes, and this is the oxygen content or the excess air in the flue gas. Here on the left-hand side, you can see the efficiency of a boiler and the oxygen content in the flue gas after the boiler. And the water content of the fuel. So as I mentioned before, the fuel quality is an influencing parameter. And when you can see here, when the water content is up to 50%, the efficiency is lower when you burn the fuel with lower moisture. And this is taken into account when you find the right settings for the combustion. And here on the right hand side, you can see the correlation between the oxygen content in the fuel and the CO emissions. So it's called CO Lambda Characteristics. And what we can see here is that the CO Lambda characteristic of a biomass combustion process it depends on the thermal power output of the combustion system. So you can see here the green line, it's 4 megawatt, and the red line, it's 3 megawatt. So you can see for these two load factors or loads of the biomass boiler, different oxygen contents have to be recognized when we want to burn them efficiently. So this is a very strong dependence how we can handle with emissions. And most of the biomass boilers are run with oxygen contents here in the range of 8 to 10% or 7 to 10%. And you can see here there is a quite big range where you can operate your biomass combustion system with low CO emissions. So I will come to this also a little bit later. Now I want to concentrate on the particulate matter emissions and why I think this is important. First, the PM emissions are identified to cause adverse health effects. So several studies clearly documented that the findings from the research over the last year see there are clear indications for this. And second, the understanding of the building mechanism helps also for an understanding of the measures for the reduction of the emissions, because by decreasing the PM emissions, also gaseous emissions and especially CO and organic gaseous compounds were reduced. So when we talk about PM emissions from biomass combustion, we have to categorize these emissions first. So there is the coarse fly ash emissions, which you can see here. These are particles with a diameter of more than 1 micron. And we have to talk about these so-called aerosols. These are particles below 1 micron. And together they form the so-called total suspended particulate matter emissions. And the coarse fly emissions are usually in a particle size range between some microns, so it's beginning here, up to 200 microns, 300 microns, but there is still no particles in this size range left. And the aerosol emissions are in this size range up to 1 micron. So as you can see in this graph, the particle size distribution is also varying by using the different fuels. So once again, fuel properties are of main influencing parameter when we talk about emissions. And you might know the term PM1 or PM10. So it means that all particles smaller than 1 or 10 microns are in these fractions. So PM1 is the sum of all the particles are in this range smaller than 1 micrometer. Okay. Yeah, for a good understanding of this formation processes, I've prepared this figure for you. So this coarse fly ashes only a minor portion of these particles were entrained from the fuel bed with the flue gas and then forms these coarse fly ashes. And the bottom ash or great ash will remain in the combustion chamber and will be discharged automatically afterwards. So I think there is another presentation today dealing with these ashes from the bottom or from the grate. Then the second part of PM emissions are the so-called inorganic aerosols. So this represent a fraction which is mainly influenced by the chemical composition of the fuel used. Why is it? Because of this so-called volatile ash-forming elements, such as potassium, sodium, sulfur, and chlorine, and also easily volatile heavy metals like zinc or lead. These chemical compounds contained in the fuel are released into the gas phase during the combustion. So here you can find the elements from the fuel. Then they were released into the gas phase during the combustion process. And by cooling down the flue gas, they form different chemical compounds like alkaline metal compounds, heavy metal oxides, and so on. And when they become supersaturated, the gas to particle conversion took place, which means that the nucleation and coagulation and condensation processes took place and forms these aerosols. So quite yeah, detailed explanation here. But once again, what's important, these forms of emissions are a main parameter of the fuel, yeah, it's first, and also of the combustion process. And to give an complete overview, there are also these carbon-containing aerosols, and these compounds are formed by the condensation of the organic vapors, which are a result of incomplete gas phase burnout. So maybe you remember the picture with these emissions I show you. There are emissions from complete and incomplete combustion, and these organic containing aerosols are a result of incomplete gas phase burnout, as well as an incomplete oxidation of the soot particles. Yeah, to summarize this formation processes during the biomass combustion, you can see here on this slide, during complete combustion, we form mainly inorganic aerosols. Here you can see a nice picture of it with a microscope. And the inorganic aerosols contain of these chemical compounds. And when we have incomplete combustion processes, we mainly form the so-called carbonaceous aerosols, soot, which is chemically elemental carbon, and organic aerosols. And especially these species are seen as health relevant. So we have to minimize especially these carbonaceous aerosols. Okay, so now we have heard a lot about these impacts on the emissions. The second section, I want to talk about the primary measures for emission reduction. And what I want to point out here is that in principle, primary measures should be preferred to secondary measures. And if secondary measures were needed, also primary measures should be included. Why is this important? So we have an effect on the secondary measures, which means, for example, when we have a small amount of particulate matter emissions out of the combustion process, also the secondary measures can be built smaller or can be operated more efficient. You have less residues like the ashes out of the ESPs, or when we have TNOx systems, we have less chemicals and additives we need. So also combination of primary, we have to look at a combination of primary and secondary measures for efficient emission reduction. So just for the beginning. And some primary measures for emission reduction are air staging processes. So here you can see on this picture a scheme of a biomass boiler. You have here this primary air combustion air inlets at different stages. You have, or we have, I have to reduce this. Oh. So something has happened now. I'm sorry for this. Did you see the screen?
Yes, we can see the front page.
Okay. So, okay.
Maybe
I have to start the presentation again.
Okay, now we are there. Ended.
Okay.
Yeah, okay. Okay, sorry for this. There will be the inlets for the flue gas recirculation below the grate, and flue gas recirculation also took place here above the grate. Secondary air inlets at different positions here and here. So air staging is quite a well-known measure and is implemented in the most combustion systems on the market, and leads to reduced emissions, especially also when we want to reduce nitrogen oxide emissions. It's a very helpful measure. So you can see here, or you can find here, the main influencing parameters or suggestions for the excess air ratios and residence times when we talk about these air staging processes. Another relevant parameter, as I mentioned, is the process control system. So the process control system have to meet the requirements of the combustion system in all operation phases. This includes startup and shutdown procedures, part load operation, as well as load changes. So the application of advanced process control systems like model-based control or CO Lambda control, some kinds of temperature control, will give another primary measure for emission reduction. And also to minimize the operator behavior, the development of an advanced process control system could significantly reduce these emissions. So I will show you, or I want to introduce a new developed control unit. It's called CO Lambda Control, and the system was developed by my former colleagues at the BEST and the German sensor manufacturer called Lambdec. The system is based on a sensor. You can see the sensor here. The sensor detects the O2 as well as the CO equivalent content in the flue gas. And then there is a form of control algorithm which suggests the best, or the best O2 value for this combustion process currently going on. And this suggested O2 content can then be implemented into the boiler control, and from the boiler control the variables who are responsible for the combustion process are changed to do this suggested optimal oxygen content. So this is just to show you there are some of these measures are still on the market now, and there are results from measurements. So there are measurement campaign over 6 months, and the results were we have to reduce the CO emissions were reduced by 200 milligrams per norm cubic meter. You can see here on this picture the CO values and the rate of occurrence of the CO emissions. So you see that the highest amount of CO emissions occur in the range here 50 milligrams or so on, and then the curve flattens. And when the CO Lambda control is not activated, the CO emissions are in this range. So you can reduce the CO emissions with this control unit, and you can also reduce the PM emissions with this control unit. You can see here. So these emissions are reduced by approximately 20%. And when we not want to talk about emissions, but we want to talk about efficiency and costs of the operator, then you can find here that the fuel consumption was reduced by 3.8% with this measure, and this is directly a cost reduction. So you will see emissions and emission reduction and cost reduction are also a combination of these two are also relevant. I think I have to look a little bit on the time. So here I don't want to go through this in detail. I will.
10 minutes left.
Okay, 10 minutes. Okay, but nevertheless, I don't want to go through this in detail because you can have a read on this afterwards. So here I will deal with this measures for the particulate matter emission reduction. You can see here what's the most important. Maybe I will do it like this. The most important is to minimize the entrainment of the particles when we deal with the coarse fly ash reduction. Then when we deal with this carbon containing aerosol reduction, which are relevant for the health effects, we have to optimize the burnout quality. And when we talk about emission reduction from this inorganic aerosol reduction, we have to look at this potassium release, because potassium is the major chemical compound for these processes going on. So what important is that the fuel bed temperature has to be kept as low as possible, because then the release of the potassium is inhibited. Okay, I think this is just to give you an overview, and now an interesting topic will be to the operation of the heating plants. So what can we do to operate the heating plants more efficiently? So I hope and I think it's just clear that the combustion technology has to be appropriately adapted to the fuel quality. So you can't burn all kinds of fuels with different moisture contents and different fuel compositions and different ash contents within one biomass combustion system. Doesn't work, or still it doesn't work with the same parameters of combustion. The combustion temperature plays a relevant role. So remember the 3 Ds. Temperature is one of them. When we have too low combustion temperatures, there we have high gaseous emissions and also a poor char burnout quality. And furthermore, the efficiency is not good. Too high combustion temperatures, then we can have problems with slagging or deposit formation in the combustion chambers, and controlled by flue gas recirculation and or cooled surfaces. This can help to keep the combustion temperature in the right window. The next T is this turbulence, and turbulence means mixing the flue gas and the combustion air and the residence time for these flue gases in the different zones. So first, beginning on the grade, we have to look that there is a homogeneous fuel distribution over the fuel bed. Then we can implement air staging or air staging processes, and air distribution will help to reduce the emissions. Then the mixing of the flue gases are relevant for a complete burnout quality of the gases. And remember, once again, complete burnout quality means lower emissions and higher efficiencies. And yeah, the mixing of the flue gas can be achieved by the design of the combustion chambers and the secondary air inlet nozzles and so on. And for designing such appropriate combustion chambers, also CFD simulations can be used, not for the operator, but for the manufacturer of these systems is an efficient tool. And the residence time of the flue gases in the hot furnace should be long enough to achieve a complete burnout of the gases. So this is just once again the importance of these 3Ds. And yeah, once again, the process control system, we have different kinds of systems. We have this load control. The load control should generate a smooth operation of the plant, so avoid stop and go or partial load operation. The combustion control should be available to have appropriate excess air ratios. So once again, too low excess air ratios will form high emissions. Too high excess air ratios, we have also higher emissions of CO. And also increased flue gas flows. This decreases the thermal efficiency. We have higher particle entrainment from the fuel bed, and this forms higher PM emissions. The temperature control is important to avoid slacking and deposit formation. So this is also a quite big problem in some biomass combustion plants. And another important thing when we talk about the temperature, as we know, is to guarantee this complete combustion and complete gas phase burnout quality. And also the pressure control is important, that we can operate the system smooth and safe. Okay, then not only the combustion system is important when we talk about emissions, also the correct dimensioning of the whole, let's say, district heating system or process system, including the hydraulic system, the buffer management, and the whole district heating network. And just to give you some ideas, look at your system temperature. You should have a subordinate control of the network. You can integrate other energy sources to reduce the hours or the operation hours of the plant, and so on.
Joachim,
yeah.
3 minutes left.
Yeah, just perfect. I think it's the one of the last slides. So some other or miscellaneous information. Just yeah, minimize force air. A lot of heating plants have this issue that they have force air somewhere in the system, and then the combustion process can't be operated at a good level. Look at your service and cleaning intervals. So especially corrosion plays a relevant role when we talk about cleaning. Sensor placement and sensor aging. Most of the sensors are not in a good position, and the sensors have to be cleaned over some period of time, and there is also a drift in the signal, so please be aware of this. As I mentioned, the CFD simulations, they help the manufacturers for the combustion chamber geometry, for example. And increase the flexibility through different measures. So there might be an interesting project called Thermoflex. I don't want to go through this project in detail, but just to show you here a few numbers and the methodology in this project. So you can see here the website. You can have a look on this website and you can find some relevant information about this project. The main aim is to increase the flexibility in the district heating sector. And by doing this, we of course have emission reduction here once again and increase of efficiency. Yeah, and this is the last slide. So it's important because alone in Austria, there are more than 3,000 district heating systems going on. And yeah, these are the partners within our project, and yeah, we want to find solutions for this district heating sector. So thanks for your interest. I hope you can I can give you some ideas for introducing into the topic emissions and air quality. You can also find my contact data here on the slide. And when you have this presentation on the last slide, you can also find the references of the pictures and so on. Yeah, I'm just in time, I think, Heidrun, and I'm open for questions if there are any. Thanks.